Welcome colleagues on today's lesson, in which we are going to focus on our next core subtopic, which is the shift theorem. So this is one of the subtopic under the Laplace transform. So what does the shift theorem say? So it is just the same idea. Let's say I say f of x. F of x is shifted. Let's say f of x is shifted by a. So this will mean f of x is shifted by a. So there is a shift in f of x by a. So this is just the same idea which you are going to find now using the Laplace transform. So now, since we know that the Laplace transform of the function f of t, the Laplace transform of the function f of t is equivalent to the integral of 0 to infinite. This is what we discussed in the first video. This is what we are going to have, like this, dt. So this is the mathematical definition of the Laplace transform. So now, what it all means is, what we mean by that, now we need the shifted version of the Laplace transform. Now for us to shift this guy, for the Laplace transform, you will intro the function that will be represented by f of t will be exponent at. This will cause a shift in the Laplace transform. So let's just go ahead and solve it. Then at the end, we'll explain how it will be shifting things. So now, since you have this, and we have this multiplying together. So let's go ahead and say that since we are having the same basis and we are integrating with respect to t, since we are having the same basis, which is exponent, we can add the powers. So this can be written down as exponent negative st plus at. Now look, let's take a moment and say that we can see that a t is common here and the same t is common here. So now what can we do? Since we have seen that, we can factor out the t as well. So we can have this, we have this, then we have negative s plus a, like this, multiplied by t dt. So now at this point, what we have is the Laplace transform of the function, e exponent at. So now let's go ahead and integrate this simplified version. So now how do we integrate exponent? So integrating exponent, we know that we are going to have this, the same thing, the way it is, plus a. We're just going to have the same thing, the way it is. Then now we are going to divide it by the derivative of the power. So if we differentiate the power, we know that we are just going to remain with this part. So what we are having is negative s plus a. So this is what we are having. So from here we have to introduce our bounds. So we know that the bounds are from infinite, from 0 to infinite. So the upper bound is infinite, the lower bound is 0. So let's go ahead and substitute infinite. So we know that once we substitute infinite, it will be exponent infinite, and we know that that is 0. So the whole function for infinite, it will be 0. So we're just going to have this negative s plus a multiplied by infinite. So we know that this is just the same as infinite and it will be 0. So for the first part, we're just going to have a 0. So we're going to say minus. Now look at this. Let me say we factor out a negative. Let's just factor out a negative so that we just say that this exponent is what is negative, so that we get to have a good denominator. So when we factor out a negative, we're having negative s plus a. So if I factor out a negative, I'll have s minus a. So this is what we are having. I'm having s minus a because I know that if I distribute it back, this will be negative s, this will be positive a. So I've just factored the negative to make my work easy, but you can still go the same way. So we know that this will be negative exponent, then we're substituting 0. So we know that everything will just turn to 0, then over s minus a. Now look at this. This is 1, this is just 1. And this negative and this negative are cancelling out. So we're having what? A positive. So this is just the same as 1 over s minus 1. S minus a. So this is the Laplace transform. This is the Laplace transform of exponent 80. Now, as I was saying, even without you factoring out the negative, let me just prove it for you. Even without you factoring out the negative, you can still get the same answer. So it was here where we were. This was the part. So where we are substituting 0. So since we know for the infinite part it's 0, then for where we are substituting 0, we're going to have exponent to the power 0, isn't it? But there is a minus. We are saying minus when we're substituting exponent to be 0. Then we are having negative s plus a. So this is what we are having. So if we distribute the negative here and here, we're just going to have 1, since this is 1, over the s becomes positive, then the positive becomes what? Negative. So we are still going to get the same answer. So this is equal to the Laplace of this boy. This is just equal to the Laplace of this function. So now what do we get to see, or what do we get to know? You understand that this, once we are multiplying the exponent in the Laplace transform, or the Laplace, the mathematical representation of the Laplace transform with the exponent 80, we are getting a shifted version where we are having 1 over s minus a. So this behavior, just a moment. Yes, so this is showing us that it is having a behavior where it is shifting whatever Laplace transform you are going to get. Just the moment you multiply it with any function, you will know that it will be shifted 8 times. So if I were to say that, let's get, if we had exponent negative 80, we know to say that in the end we're just going to have 1 over s minus, then what is our a now? Our a is negative a. So where there is a, we'll be putting what? Negative a. So in the end we're just going to have 1 over s plus a. So either way, if you are just seeing this, we know that it will be shifted the number of a's it has. So if on a we had 2, we're just going to replace, instead of a we're going to say negative 2. So if it was just 2 without a negative, it was just going to be what? 2. So now, us knowing this, coming to knowing this fact, you'll be finding let's do this example. Let me just clear off the board. So you'll be finding example questions like this. They will be asking you to say you are required to find the Laplace transform in this form. The Laplace transform, then they say t. So now, if I were to ask you to say find the Laplace transform of t, we know that this is going to be 1 over s. Due to the previous videos which we shared together. Now, since we know that, now look at this. This only gives us this, but this is a shifted what? This is a shifted version. So we just know that we are going to have the same thing, but it will be shifted how many times? So minus to be shifted 8 times. So we are going to have a. This goes on to say the Laplace transform of t squared. We know that this is going to be what? 2 factorial over s to the power. This is s to the power 3. And excuse, even here, this is s to the power 2. So this being s to the power 2, we are going to have power 2 there. So if I say find the Laplace transform of t squared multiplied by exponent like this, so we know that this will be shifted. This is going to be shifted. So we are going to have 2 factorial divided by, so s will be shifted down 8 times. So we are going to have s minus a to the power 3. So this is technically what the shift theorem does. It will help you in determining the shifted versions of the Laplace transforms. So let me just give you some questions. For you to try and send in the group as well. So for the first question, I would require you to find the Laplace transform. The Laplace transform of t to the power 3 exponent 80. Then the second one, the Laplace transform of t cubed as well, exponent negative 80. Then the last one, I would want you to find the shifted version, the Laplace transform of sine bt. So this was it concerning the shifted Laplace transforms. I will release another video with more questions and us starting a new topic as well, so that we'll be able to reach where we'll be doing. We'll start with the inverse Laplace transforms. From here, we'll do 2 to 3 questions. Then we'll go on and start doing the inverse Laplace transform. Then from there, we are going to see how we'll be applying this in derivatives. We're going to apply these in ODEs, which is ordinary differential equations. So we are going to see how we'll be applying the Laplace in ODEs. So before we do that, we need to know how to solve the inverse Laplace transforms, of which it is just a build-up from here where we have ended. Otherwise, this was it for this video. Bye bye.